Good afternoon, everyone, and welcome to today's Lunchtime talk. A warm welcome on this cold summer day. Before we start, on behalf of Maritime Museum Tasmania, I would like to acknowledge and pay our respects to the Palawa Pakana peoples as the traditional and ongoing owners and custodians of the skies, lands, and waters of Hydrographic. We pay our respects to the elders, past and present, and acknowledge that sovereignty has never been ceded. So unfortunately today, Roger Proctor was unable to be with us because he got ill. But we are very fortunate to have Tidetech co-founder Penny Haire stepping in at short notice. Thank you, Penny. And Penny brings more than 20 years experience as a skipper and as a navigator with specialist expertise in electronic navigation. At Tidetech, Penny works on the intersection of science and the maritime world, helping translate complex oceanographic data into practical information for sailors, commercial operators, and recreational users. And yeah, we are delighted to have her with us today. So please join me in welcoming Penny. Thank you.
Hello. Good afternoon, just, isn't it, I think? Very nice to be here. Actually, Roger and I were fighting over who was going to do this because, of course, talking about tides is our favourite subject, especially to, I suspect, is a fairly informed audience living by the sea, as we all do. So this talk's going to be a little bit technical in parts, but hopefully some things you may not have known before about the tides here and also around the world. So I'll go straight in. Just a little bit about me. My background is as a sailor, really, since I was about 19. As my mother keeps reminding me that I ran away to sea, so I dropped out of uni and went to work on boats like these here on the left. Eventually I got to be a skipper for this boat here on the left called, at the time it was called Ocean Spirit of White, an 80-foot boat taking young people to sea for sail training. So that was great fun. Eventually I ended up as chief instructor for the Royal Yachting Association in the UK, and I was a trustee for the National Maritime Museum for 4 years before I came to Australia, 2004. And Roger, who's not here, this is his slide. So Roger is a very eminent oceanographer, particularly when it comes to tides. And he worked for many years at the Proudman Oceanographic Laboratory at Biston Observatory near Liverpool. Liverpool, as we'll see in a minute, has some of the biggest tides in the world. And it was a really, really important place back in the day. It was somewhere where chronometers were calibrated to the sound of a gun at noon, or local chronometers. And it's where a lot of the, well, of course it was an astronomical observatory at first, and then it became the centre for tidal expertise. So two people in particular, Joseph Proudman and Dudson, I'm sorry, I don't know his first name. In the back there, that machine is a tidal prediction machine, and I'll show you how that works a bit later. Now Proudman did the first computerized tidal model of the waters around the UK. When I say model, this is a mechanical model, not a computer model at that time. And these machines were used to predict the tides exactly for D-Day landings. So it's, extremely groundbreaking and important laboratory. And then it went on to actually be the inventors of, or progressed into computers. So initially on paper tape, and Roger is old enough to still remember programming on paper tape that used to have to go off and be to the big supercomputer somewhere else and be programmed to do a model run. then eventually magnetic tape, and then supercomputers. These days we can run calculations on a laptop. These are the tides at Liverpool, and as you can see, they're quite large, so up to 10 metres in tidal range. The tidal range is the difference in height between low tide and high tide. And so there's a lot of water moving around. Incidentally, I actually grew up very near there as well. I didn't know Roger until I moved to Australia. But so I grew up about 15 miles from Liverpool, and I've been fascinated by tides my whole life as well. One of the things we used to do as kids is to walk out to this island at low tide, that picture on the right, when it was complete, you can walk out through the sand flats, and then at high tide, the tide will come in and surround you, and you were stuck on the island until the tide went out again. It was great. It's a lovely thing to do. So, how do tides work? Is anybody here a sailor or a mariner? Any hands up? Yeah? A few in the room? Is anybody completely new to tides and how they work? Not so much. Yeah, okay. Well, basically, it's almost all of the tides that we experience are due to the gravitational pull on the Earth from the Moon. So that's the image or the video on the top left there. And effectively, the Earth spins under the gravitational pull of the Moon, or they actually rotate around each other. And that creates a bulge of water facing the Moon, and also a bulge of water on the opposite side, which is like a sort of centrifugal force which pushes the water out. So if there were no land masses around the Earth, that means that everywhere we experience 2 tides a day, 2 high waters and 2 low waters. Now, when you add the sun into the mix, this is the bottom right, then once a month, the sun lines up with a full moon, and you get what's called spring tides. And then when there's no moon, the gravitational forces line up again, and you get another spring tide. So we get spring tides, what you hear called king tides, every 2 weeks. And then opposite, when the forces oppose, in other words, when as you can see in this diagram here, just there, so half moon, neap tide, that's when the forces are split a bit, so you get smaller tides, a smaller tidal range. So if you remember, half moon is neap tides, so smaller tides. A full moon and no moon is spring tides or king tides. Incidentally, if you're wondering where the word spring comes from, we don't only get spring tides in springtime. It's actually from an old English word called springen, which means bountiful, bursting forth, plentiful, as springtime is. And I suppose that's where the word spring comes from. Whereas neap, it comes from the Old English word neapth, which means poor or impoverished. Like the Scottish have a vegetable, like a turnip, it's called a neep, which is a bit of a mean vegetable that's kind of watery and not very nice. So springs and neeps, that's their origin. So Hobart. We have a really quite strange signal here compared to Liverpool. Liverpool's quite regular. This is neap tides, you can see on the left. So you have almost equal tides twice a day, but as you go towards springs, then the first high water of the day is much smaller than the second high water. That's called a mixed tide. Now I'll come on to why we have that in a minute. So it can make it a bit confusing, because you can have two high tides a day, but one of them is only half the size perhaps of the main tide. And around the world, there's all sorts of different tidal signatures. So in Boston, Massachusetts, that's in the Atlantic, that's called semi-diurnal, twice a day, fairly regular. The high tides each day are roughly the same in height or in range, and you get bigger tides at neaps and springs. Then, where are we? Bottom right, you have diurnal, which is once a day. That's in China, in the Pacific Ocean. There's a reason for that, and I'll come on to. And then you have mixed tides. So you can see actually bottom left there and top right, they're both mixed diurnal. Or mixed and mixed diurnal. So you can see there's all sorts of irregular tidal signals. So you have to really look at your tide tables to see what's going to happen, because one tide can be much different from the next tide. So the things that modify the gravitational effects of the moon and sun are the shape and size of the oceans, how deep they are, how big they are. And then if you imagine the gravitational pull, it's like pulling up a huge lump in the ocean and letting it go as the moon passes. A wave then propagates to the edges of the ocean. And as it reaches the edges, it enriches the continental shelves. It steepens, just like a wave on a beach. And that's where you get most of the tidal signal. You don't really experience much tide in the big ocean, the deep ocean. It's on the edges where we see tidal forces, or tidal heights and currents increasing. And of course, add the Coriolis force, which is a spin of the Earth, that will rotate the way that the tides work as well. So it's quite complex. Just to illustrate kind of how this works, it's really actually down to basic physics. You might have seen that trick where an opera singer can break a glass because they can sing the same note. It's called a resonance, so a resonant frequency. And so I'm just going to get this video clip going. So here's an oscillating force. Imagine it's kind of like the moon, but the moon's to the right. This might be, say, the Atlantic Ocean. And you see how they're out of phase with the oscillation. But the shape and size of this ball here exactly matches the frequency of the oscillation. It's crazy, isn't it? And that's why different ocean basins have different tidal regimes. This is how they match the resonant frequency of the shape and size of the ocean. Oops. Right, so the Atlantic, the resonant frequency of the Atlantic is 12.5 hours, so twice a day. That's why you saw in Boston, and also pretty much everywhere around the Atlantic, you get 2 tides a day, very similar tides in height and range, and gradual progression to springs, up from springs to neaps and back again. Whereas the Pacific Ocean is 1 tide a day. And where you have I guess an interface or an interaction between the two oceans, you get a mixed tide, a bit of both. And that's what we have here in Hobart. So we have a bit of Pacific influence and a bit of, or actually Indian Ocean influence. And that's what gives us our slightly strange mixed tidal regime. And around the world, that's what it looks like. So semi-diurnal, twice daily, is in red. And you can see that's largely around the Atlantic. Diurnal is once a day, so Western Australia, up towards Northeast Asia, and actually also slightly in the Gulf of Mexico, and then mixed is everywhere else. So yeah, it's quite an interesting regime. Actually, it does say here it's semi-diurnal. Well, it is, but it's also it's a bit of an oversimplification. It does have influence else from other regimes as well. So just to recap, top right there, diurnal is once a day, semi-diurnal is twice a day, and mixed is a mixture, I suppose. Right, now, that's all very well thinking about how these oceans work, but because the Earth's spinning, that wave I was talking about, as it propagates out, starts to turn because of the Coriolis force. Same reason why our weather systems will rotate, high and low pressures rotate. And so they rotate around a node, which is like the middle of the spider's webs. And so that's we're coming now to how we actually calculate tides on a global basis. So you can imagine, let's say, the nearest one here with a dark blue dot. So high water will, in terms of time, will circulate in a clockwise direction. So at each time you step to another white line, high water will be an hour later until it comes round again. And the further away you get from the centre, the higher the tides will be. Rather like imagine sloshing a gold pan, where you're sloshing it in a circle of motion, and it's very shallow in the middle but deeper around the edges. Am I getting too technical here? Is everyone still okay? Any questions at this point?
What makes a node? What's the special thing about a node?
It's a very good question, and I wish Roger was here. My understanding is that it's because of the shape of the ocean basin and the resonance, it's where things end up settling. There's nothing to do with any kind of ocean peak or anything like that. It's just simply the relationship between the land, the shape of the ocean, its depth, and all the other gravitational and Coriolis forces. Yeah. But that's a good question, I'll have to remember that one. So how do we predict tides? Well, traditionally, we have had tide gauges at ports. So when you go to your tide tables, you'll probably see Hobart tide table, which gives you high and low waters out for next year or whatever. And those have been derived from years and years of measurements. Okay, so these are measured by tide gauges, and you've all been to Port Arthur, I imagine. Well, there's a very, very old and very, very important tide gauge at Port Arthur on the Isle of the Dead, and it's a line carved into the rock with a sort of symbol underneath. And that was the first tide gauge that was established in the early settlement days. And it's, conversely, it's actually really important now for measuring sea level changes because it's geologically very stable. So it's still a reference place for the whole world with respect to sea level, unchanging sea level. Anyway, so tide gauges over the years have gone from a simple float in a tube to sophisticated ones now, which are using radar. So there's a radar instrument on the end of that boom there, which sends radar waves down to the ocean and receives them back, and the time taken effectively will be, the height will be derived from that. To get the complete tidal signal, all the information you can possibly have, you need about 18.6 years of records. It's quite a long time. And the reason for that is the period of time which encapsulates all the astronomical variations. So, now it's getting a bit technical, I'm sorry, but it's also quite interesting. I didn't know any of this, and I've been sailing for years, I had no idea. I heard of harmonic predictions, but I didn't know what it meant. So, harmonics, what's that? It could be music, couldn't it? Well, these are all sine waves. There could be somebody plucking a string. Actually, what they are is tidal components, if you like, or constituents. So the top one there, M2, is the principal lunar semidiurnal constituent. That's the thing that gives you 2 tides a day. And if it's strong where you are, then that's going to be the main signal that you see. And then you have S2, which is the sun. So if you're in Northwest Pacific, diurnal tide, that one would be stronger than M2. And then you go on down to the sort of minor constituents, some of which are created from the larger ones. Don't ask me how. But you end up with a set of all these curves which are then put together to give you a tidal prediction. So when you have all these 18.6 years of measurements from a tide gauge, if you analyse those measurements and you can get rid of all the noise caused by weather and so on, then you can extract and tease out these individual tidal constituents for a port. And that's been done for all the ports worldwide, about 5,500 ports worldwide, where there are tide gauges. And that's what you end up with, is a set of constituents. There's about 400 of them, identified constituents, and some of them are really, really small. So the smallest one, its wavelength is 18.6 years. Imagine, and it's, it's only a little, but it still contributes. In some places it becomes quite important. Mostly, if the tidal range is less than 4 metres, you only need about 16 constituents to reasonably accurately resolve and predict tidal rise and fall at a location. We did a exercise a couple of years ago where we took the tidal signatures for various ports and we turned them into a note. Because if you think about it, if you compress this wave at the bottom to an audible frequency, like thousands and thousands of times, it becomes a note, a harmonic, I suppose. Just what we're seeing is in the wider picture, the time that these physical phenomena take to play out. It's extremely low frequencies, several days, weeks, and months and years. So what we're going to do now is we're going to look at the tidal machine. So you remember that machine I showed you in the first picture? You can see at the bottom there, M2, that's say the lunar twice a day constituent, and then there's the sun, and then there's other constituents at that port. So what happens is the operator of the machine would know the size of the constituents for the port they're looking at, and they would set the machine for that size. So you can see top left there you have a big M2, relatively small at S2, and then K1 is a certain size. And then once the machine is running, that actually prints out a tidal prediction according to the size and speed of those constituents. It's pretty clever, eh? So those settings will be different for every port in the world. And so, for many years, somebody would have a paper roll and a drum, and as it was turning, they'd be recording the time at which the graph was at its highest. And that's how tide tables were originally produced. Oops, yeah, that's the tidal machine there. Right, now onto the ocean. So we've done tides a fair bit, and so we're going to talk about ocean currents. Completely different. They do mix a bit with tides on the edge of the continental shelf, but ocean currents are driven by completely different forces. So this is a map by Benjamin Franklin that he drew after he crossed the Atlantic to go to France and back. And here's his portrayal of the Gulf Stream as this kind of superhighway going northwest from the Gulf of Mexico. And he was, on average, he wasn't wrong. But of course, the currents are much more complicated than that. And these are the major ocean currents around the world. Here in Tasmania, we're affected by the East Australian Current, which I'm sure you've heard of. And that ends up coming down the east coast of Tasmania and mixing with the Southern Ocean. There also is a current that's not mentioned on here called the Lewin Current, which comes around from Cape Lewin in Western Australia, around the Bight, and down the western side of Tasmania. It's weaker than the East Australian Current, mind you. And so these are three-dimensional structures. It's not just surface flow. So you have cold upwellings coming from the depths, and then warm downwellings. It sounds odd, I know, but it's a great mixture of these enormous conveyor belts going around the world. And so it means that the oceans aren't isolated from each other. There is transfer of water and all it contains between the oceans. But this is actually what happens. This is a simulation of ocean circulation from NASA, where they did a several-year run. You can see the time up there. It's a bit out of date now, but it shows you the complexity of how the ocean changes month on month. So watch the month clicking over there. My favourite bit's coming up in South Africa, where you have the Agulhas retroflexion, very strong currents coming down the east coast of Africa that hit the Southern Ocean, and it pushes the currents back the other way. And a bunch of eddies head off into the Southern Atlantic. There's Madagascar, and then as we come into Northern Indian Ocean, it's very active around the each side of the equator. And then down, hopefully down towards Australia. Oh, come on. Then the Kuroshio current, which goes up from Philippines right up to Japan and beyond. So it's extremely complex, as you can imagine. And if you're a ship or an ocean sailor, you really want to know what's going on, because you could be pushing really strong current when it could be with you if you perhaps altered your course a bit. So, how do we measure currents? So, not very far away at IMAS, at the university in the big building on the waterfront, they have lots of programs running to coordinate the observation of the seas and oceans around Australia. So it's the Integrated Marine Observing System. And Australia has one of the best, if not the best, observation systems in the world. There's been a lot of resource being put into it, for good reason, because it affects all of our lives and our prosperity and the environment. So we need to know what's going on. And measuring the ocean is really expensive. They lose a lot of things because of bad weather and so on. But they have satellite observations, moored buoys with instruments underneath, gliders, these Argo floats which go down to the depths and come back again, drifters, CTD carousel. I'm not sure what it is. I think it's to do with salinity and conductivity. And they even stick instruments on animals as well. I'll come to that in a minute. So it's quite sophisticated. And all these observations go into improving and informing our science and the ocean models in all different aspects. Here's an example of elephant seals. So the little tracks there are a seal. Each one of those is a seal, going from Antarctica or the Kerguelens, South Georgia. And you can see the temperature of blue is getting colder as they go towards Antarctica. So on the left there you can see a male elephant seal with an instrument on its head. And apparently they've observed that having this instrument on its head makes it more sexually attractive to the females. So there you go. And drifting buoys, so these Argo floats are amazing. They sink down to the depths, right down to the bottom of the ocean, measuring as they go. Then they'll pop up and then transmit the data to satellites. And there's several thousand of them around the world. And they're very, very important to understand the three-dimensional structure of the ocean. Actually, what was that? Yeah, that was last month. Only one day. It's not going on. The other thing which is increasingly important is measuring the height of the ocean from space, called satellite altimetry, So these are radar-like instruments on satellites, which measure the relative height of the ocean. So is it greater or lower than the mean? It has all sorts of implications to do with sea level rise, principally, but also ocean circulation as well, as I'll show you shortly. So these are the satellites which have been adding to our knowledge of the of how the ocean works. And what we're seeing now, I hope, is an increase in detail over time as new satellites get added. I've not seen this in some before, actually. But yeah, look at that, that's amazing. That's Topex Poseidon. So these instruments take a snapshot of the ocean, I suppose. This latest one, SWOT, is very exciting because it has much better coverage, so we can get a snapshot of the ocean much more frequently and in better detail than we've ever had before. So that tells us where the eddies are and what they're doing. Very important for shipping and for many other kinds of studies. So what we do is we get the stuff that's thrown away. So when I say we, I mean at Tidetech. So we get the satellite observations of sea surface height, and we want to know what's happening at the edges, because that's where the tidal signal is. And so what we've been able to do, using some other people's work, Oregon State University principally, is to derive a tidal height map of the oceans. So red is high tide, and blue is low tide. You'll see in some parts, like around the UK, there's a darker red colour. Similarly, in northwest Australia, that's when the tidal range is bigger, some bigger tides. It doesn't show it that well, but it gives you the idea. And you can see with circulation around those nodes. If you sort of get your eye in, you can see where they're rotating around. So So global ocean models will take in all these data and then produce a forecast. You might have heard of weather models. So the weather forecasts we use are developed from atmospheric models. The same physics applies, but in the ocean. Fortunately, the ocean moves much more slowly than the weather, so it's a bit more accurate to predict ocean currents out for a few days. And tides are inherently predictable because they're caused by astronomical forces. So forecast out to 7 to 10 days are reasonably good now. What we do is, I try not to plug too much, but I thought you might be interested in some of this. So we get information from the global ocean models, and we do our own tidal models as well. So Roger's an expert at hydrodynamic tidal simulations, and we make this available through all these data services to customers. So an example is we have, is that a video? Oh, it's a video, good. A tidal model of Singapore Malacca Strait. This is here, Derwent Estuary. And you can see there's some pretty big tides around the top of Brunei there. That's South Brunei. And at the south of Brunei too, there's a mixture too with the Southern Ocean currents too, so there's a bit of mixing going on. We've also developed a model for the Whitsundays, so a very high resolution, 100 metres, and we're hoping that's going to be picked up for the Olympics coming up. We're working with the Australian Hydrographic Office at the moment to develop new models around Australia for a new standard that's coming in. So that's good. Where are we? Right, so back in the day, 2013, we developed a really detailed model for the 34th America's Cup in San Francisco, so which was picked up by the organisation and was used across the whole event. And here's a bit of TV footage and they managed to overlay our tidal data onto the TV course, which is cool. What you're seeing now is one boat out to the right, I think, one into the left. So the one out on the right, Italy, is going out and getting adverse current, whereas the Swedish boat inshore is getting positive current. And we could see, in real time how that distance between them was decreasing because they managed to make the right decision about which way to go. So that was pretty cool to see. It's nice to see things actually helping people in action, even if it is rich billionaires. But anyway, they did a really cool job of putting the data on a graphic like this to help the public understand what was going on. So we're involved now with a number of other companies who use our data for reducing fuel use and emissions for shipping. So let's see, have I got I've got video, good. So this is a vessel. Now the shortest distance is the blue line, but the optimum distance is the purple line, because that vessel's used tidal data from around the UK and then ocean current data. So it's used less fuel, considerably less fuel, and therefore lower emissions, and they make a cost saving as well. So it's win-win. So all those complex eddies you saw earlier in that big global map, that kind of information is being used in this setting. So it shows you how technology has really fantastic practical uses. And for us, decarbonisation is a big motivation for what we do. We'd rather do that than give data to billionaires, but anyway, at least they pay, I suppose. Sorry, this slide's a bit busy. So we're working with a company called Deep Sea Technologies who do AI. I know it's very, very trendy at the moment, but they do some quite clever things. They have to understand the ship behaviour, in other words, how it responds in different wave and wind and conditions, and they measure fuel flow and so on and so forth. Then they make this kind of what's called a digital twin of a vessel. So this digital twin should respond in the same way as the actual vessel itself. And then they use our weather services and current services to compute sometimes it's the right speed, because often ships are constrained, they can't go left or right of a straight line. So it's getting the right speed to arrive on time, and not too late or not too early. That's really important. That's also the optimum route. And so one single trip there, Tokyo to Singapore, on 5 years, is a saving of $12,000 of fuel. So that's pretty significant. The other thing we're doing is we have a contract with Apple. Anybody got an Apple Watch, by any chance? Okay, I've got one here. So Apple built an app around our data. So we made this global tidal surface, which predicts tides out to 7 days, everywhere in the world, every 2 kilometres inshore. So what they've done is, rather than having tide at your nearest port, it's where you are. So that's quite an innovation. So anyone with the watch, they go to the app, it'll work out where you are from your phone, and it'll give you the nearest tide at the nearest beach. So yeah, it's really handy, actually. I've used it myself quite a bit when I've been boating. They're a very strange company to deal with, I can tell you. I've been negotiating with them for a year. I'm not afraid of negotiating with anybody. They were... Anyway, that's another story. The other thing we're doing now is getting our data onto ships' navigation systems. So those orange arrows, they're not very legible, but they're showing the tidal currents in the Gibraltar Strait. Oh, and the next, I'm skipping over that slide because it's a bit technical, but the next innovation is these kinds of data being mandated for ships. So there's this new standard coming in, because shipping companies are the slowest and meanness to do anything if it means spending money. So it has to be mandated. So that's coming in 2029. So we're hoping to do well out of that, but we'll see. But it's pretty cool. It means that the navigator is going to have the current information at their fingertips. And you can see this sort of contour, that black line that's changing. That's a safety contour for the ship, showing where it can and can't go. And that's responding to the tidal height prediction. So rather than having tide as just a point, as people have now, at a port, it's everywhere. So it's tidal height across the whole field of view. Oh yeah, this one. How am I doing? Oh, not bad. So this actually is how we started. In 2008, Roger and I got together because my job at the RYA was coming to an end and I needed something else to do. So I thought, well, it's strange that there's no information that I can find about tides and currents here in Australia. So I contacted the Proudman Oceanographic Laboratory, and they said, I should talk to Roger, he's in Australia. So that's how Tidetech started. So Roger got hold of some data from IMOS, CSIRO. He turned it into a digital file. And then I ran the dock in Sydney at the start before the race, trying to sell people USB sticks. So. And it worked, actually. We got Quest there. We had 15 boats signed up, and we got the winning boat, which is Quest. And Wild Oats as well, they used our stuff. So that's what started us as a company, actually in elite yacht racing. And that we've been able to get as far as we have without any external funding or anything, just by making money as we go from these kinds of things. Yeah. It's not been easy. And this is what I did an optimization for last Saturday. And so on the left you can see the currents, which are more or less replicated on the right. So there's a big eddy going anti-clockwise off the north key coast of Tas. Then there's another big eddy above that off Green Cape, or Gabo, off New South Wales there. So with the winds being where they were, coming from the west, this vessel was a TP52, so fairly common racing yacht. The direct route, shortest distance, is the black line, but it's definitely worth them going out and getting into that big eddy off New South Wales before coming in towards Tasmania there. And they also cut a free ride off that second eddy at the bottom. And that's quite often the case. You see this sort of chain of eddies that get spun off north of Sydney and end up travelling down the coast in like a chain. It's kind of continuous. That's it, I think. Will it will again? I don't know. We'll see. We've had, I think we've had the, oh, there it goes. I might have to click the animation. Yeah, so I think we've had, at one point we've had about 50% of the fleet. We've had about, I think, 70% of the handicap winners and about 90% of the line honours winners. Line honours is the biggest boat. So, there we go. So, any questions?
Thank you.
There we go. Oh, yes. Yes, sir.
I mean, back 100 years ago when I applied, when they started the computing machine, were they analysing the data and trying to work out what frequencies and so on? Or were they looking at the almanac for period of the sun, moon, and all the rest of it?
That's a very good question. So the first tidal machines, I think what was it, a Babbage engine, that might have been it. It was, I think it's in the National Maritime Museum in the UK, but what first thing to do is to record. So a tide gauge will give you this really long time series, years and years time series of rise and fall, and essentially, a continuous record of what the water's been doing. And that is a very, very long combined sine wave of all these different components. Now, sometimes the tide's higher than it is predicted because of weather. So a big storm will pull the water up. You've got a storm surge, I imagine. And a big high pressure can push it down. So you need to be able to get rid of that noise. It's called residual. That's what's left over. So the scientists use something called a Fourier analysis to tease apart the constituents from that mass of data. And that gives them then values for the constituents. So once you've got the observations, once you've analysed them, once you've obtained the constituents, then you plug your constituents into your machine for the location of interest, and they're going to be different values, and then you run it, and then you get a tidal prediction. So, yeah. Is that clear-ish?
I mean, the Fourier analysis and so on would point towards the major constituents.
Yeah.
And I'm just wondering whether it was fine-tuned to align with the exact period of the sun revolving and the moon around the Earth and so on.
They are related, of course, because the gravitational effects are what causes it all. But you can't rely on those alone, because you need to understand what happens with the resonance in the ocean basin you're in, and funneling effects. So, for example, in the English Channel, this tidal wave comes in to the continental shelf, which is a long way offshore. It creates this wave which gets bigger and bigger, and then it gets funneled. So that makes it bigger even more. So the land effects are very, very important, and they're very, very specific to a location, which is why you need to measure at that location. Sorry, you said nothing.
For those of us doing the VDL circumnavigation, thank you very much.
Oh, of course, pleasure.
Supporting and sponsoring. I mean, this has been eye-opening. This is fantastic. So, will we get the sort of picture on the right?
Yeah. So what we've set up a little
bigger scale, because Bank Strait, Northwest Tas.
Yeah.
The bits we really want to know about, I guess.
Yeah. So we, like last time, we were setting up a little website for the event. So you can look on your phone or laptop, whatever, and it'll draw a map of the currents, and you can step forward or backwards in time and see what's going to happen.
Right.
And they'll have weather and waves in there as well. So.
And is wind integrated into that as well?
Yeah, there'll be a wind layer which you can display. There's no routing or anything, but it's going to be just each individual component, the tidal.
About comfort.
Exactly. Yeah, I did it myself actually in 2019 with Pete Lewis. It was really, really good. Very enjoyable.
Well, I've got two questions if I may. One
Sure.
is, when there's a major event like the tsunami Arche in Indonesia a few years ago, how long does that slot remain?
I don't know. It's just so, because it's completely different science. Roger could tell you, I'm sure, if he was here, but imagine it like being like a huge wave which propagates. And the further away you are from the epicenter, then I guess that wave's got a chance to lose energy. But if you look at Indonesia, remember Banda Aceh, there's quite complex geography around there. So I think that caused some local, steepness and so on. But it's so different, because rather than being a wave which is pushed or pulled up and dropped, it's actually there's your the fault, if you like. So one bit of ocean does this suddenly, and that's made the water go or whatever. So it's a whole slab as well. It's not just, you might have seen the videos of this wall of water coming into a beach, and how beforehand the tide goes way out. There's this giant wave, and it's really kind of slab-like. As for how long it persists, I'm sorry, I don't know. I'll have to take that question on notice. Is that what politicians say?
It's sort sort of relevant, but I wonder if anybody use this sort of information when they're Melbourne to Osaka race? Because we've got a lot of little areas there, haven't we?
Yes, we have actually supported that race in the past. Yeah. So, anybody else? Good. Well, thanks very much for your time. It's a pleasure. No, it was good
You
fun.
made it really easy to understand.
Thank you. Thank you. It was good practice too for me. Yeah. So, it's nice to meet you all, and I hope that you